All right, Algebra 1, welcome to 2.4, solving equations with variables on each side. So before this, you guys, we solved equations with one variable, then we solved equations with two variables. Now we have a variable on each side of the equal sign. All right, so that's what we're doing today. So right away, guys, what I often will do is show people like why we do this. Why are we learning this? Oftentimes in the very beginning of your book, in the very first section, it'll give you a little bit of an interesting word problem that relates to like where you might use this in the world. So I thought this one was okay. It says the price of a product you are buying is $3 a unit plus a $1 flat rate stocking fee when it's in the store. If you buy it online, the same product is $2 per unit plus a $10 flat rate shipping fee. How many do you need to purchase online in order to get the same price as if you were to get it in the store? Come up with an equation for each scenario and set them to equal each other. All right, so for the first one, you guys, if I'm buying something in store, okay, I know it's $3 a unit. That's not going to change. I know that it's $1 flat rate stocking fee. I know that that's not going to change. So what I'm going to do, that 3 and that 1, those are going to stay constant. Those are numbers that I know, right? But I don't know how many units I'm going to buy. So I can say $3 times some number of units, right? So I can call it X. And the reason I'm multiplying here is if it's $3 per unit, let's say that we had 3 units, right? That's 3 plus 3 plus 3, or 3 times 3, right? So I got to plug a 3 in for X there, and you would get 9. So you know, when it's $3 per something, we're going to multiply that thing out, okay? And then it says plus a $1 flat rate stocking fee. So it's just flat rate, it's $1. You know, if I bought 10 of them, it's still just a $1 flat rate stocking fee. So we're going to say 3x plus 1. That $1 doesn't change. Okay, there's no variable with that one. Because it's flat rate and it's not like per item, right? Then on the second one, for online, and they said to make these equal to each other, it's $2 a unit. Okay, so we're thinking about the same thing here. These units are, you know, maybe we're buying, I don't know what we're buying, some kind of fancy pen, I don't know. So for this one, it's just 2x. X represents the units that we're talking about, okay? But there's a $10 flat rate shipping. So if I bought 1,000 of them, it's still only $10 for shipping, right? So it's just plus 10, okay? They want to know at what point are these equal, or what does it say here? How many do you need to purchase online to get the same price? Yeah, so at what point are the two equal to each other? Okay, so for this, you guys, I'm going to show you now, okay? The whole point of the lesson for today is so that we can solve this type of problem. So I will solve it for you right now, and then I'll go through how to do it. But I'll kind of talk it through right now. So I want to get all my variable terms to one side. Okay, so I'm going to subtract 2x from both sides, because right now that's being added, even though there's not a plus sign in front of it. That's what's happening. So if I subtract 2x from both sides, this goes away. I'm left with x plus 1 equals 10. Okay, then I want to get this x by itself. So then I need to subtract 1 from both sides. And what I'm left with is, let's move it down here, x is equal to 9. Okay, so we need to have, if we bought 9 units, it wouldn't matter if it was in the store or online, it would be the exact same price. Okay, if we go beyond 9, perhaps you could guess what would happen. I believe online becomes cheaper and cheaper and cheaper as you increase your volume. Anyway, steps to doing this. So first thing we're going to do is we're always going to simplify each side of the equation, maybe using the distributive property if necessary. So if we have something like 2 times x plus 3 equals 20x minus 1 or something like this, we're going to distribute this out and simplify it as best we can on either side first. Right, so that would become 2x plus 6 by the distributive property. So something like that, right? So we simplify first. Then we're going to combine terms of variables to one side of the equation like I did. So I would move this 2x over here, right? and then I would move the things that are not x's to the other side. So we just kind of shuffle things around, if you will, to get the x or the variable terms on one side and the non-variable terms on the other. Then we use multiplication or division to solve it. So let's look at what one of these looks like. I don't know why we're starting with example 2, but let's go ahead and do it and then we'll go to example 1. So for this one, we're going to distribute this out first. Maybe because it was a nice distributive example. Maybe that's why I did that. Okay, so we're going to distribute this out first. So we get 30m minus 18 is equal to 1/3 times 24 is the same thing as 24 divided by 3. So that's 8m, and then 1/3 times 12 is 12 divided by 3, which is 4. Okay, so I distributed. That's step 1. Simplify by using distributive property if necessary. Now I want to move my variable terms to one side. So I'm going to subtract 8m. Notice I'm going this way. I could have gone the other way. I don't like dealing with negative variables, so I always like to move the smaller one to the other side. It doesn't matter which way you move it, though, as you will see. So if I do this, this goes away, and I get 22m minus 18 equals 4. Then I got to move the 18 over. So what was happening between the 22m and the 18? Subtraction. I am going to add 18 to undo that, because negative 18 plus 18 goes to 0. I'm trying to make that go to 0. So that I'm left with 22m on this side is equal to 22 on that side. And then the final step, use division. Right? So the last thing that's happening between this m and the 22 is multiplication. So I'm going to divide both sides by 22 in order to get m all by itself. That's the goal. And it says m is equal to 1. All right, so let's kind of jump backwards a little bit and do a little simpler one, and we'll build ourselves back up to that. So here, same deal. Right now, both sides are simplified as best they can. Okay, so what I'm going to do now is I am going to move my variable terms to one side. So to do that, I'm going to subtract 3w from both sides. Okay, when I do that, this goes away. And on this side, I have 4w. And on this side, I only have 2 left. Okay, then to get w by itself, which is the goal, okay, we have to divide this by 4, because right now it's being multiplied by 4. So if I divide by 4 on both sides, I get w is equal to 1/2. All done. Okay, 1c brings in some fractions. All right, I want to just be really clear with fractions here. If you see x over 2, that's essentially taking one thing and cutting it in half, right? Whenever you divide by 2, it's cutting it in half. So if you see something like this, you guys, you can always rewrite this as a fraction with the x on the outside of the fraction. So x over 2 is the exact same thing as 1/2 x. Right, so if it helps you to see it that way, great. Sometimes we prefer it the other way, but it really doesn't matter. They mean the same thing. Okay, so I want to get you used to that. So we have this kind of setup going on. All right, so we still want to get the x's to one side here, right? So what I'm going to do is I'm going to move the smaller one, which is a 4th, okay, because it's a fraction. So a 4th of something is smaller than a 1/2 of something, right? So what I'm going to do is, right now, this is being added, right? It's plus 1/4 x minus 6. It's positive. So we're going to move the term over by subtracting it. So we're going to subtract 1/4 x from both sides. Okay, if we do that, this goes away, and then a 1/2 minus a 4th is just a 4th. Okay, so if you needed to see that, 1/2, okay, we know that 1/2 minus a 4th is a 4th. Typically, like we have that down. But if we wanted to refresh fractions here, if we're adding or subtracting fractions, we need what's called the common denominator. So another way that we could write 1/2 in fourths, right, because we want a common denominator, would be by multiplying this by 2 over 2. Okay, when we multiply by 2 over 2, 2 over 2 is just equal to 1. And 1, if you multiply anything by 1, it never changes its value, right? So I can say that 2/4 is the same as 1/2. If you think about it like this, you guys, okay, here's a half, right? So here's a half. Let's just call this a slice of pizza. half a pizza, right? It's taking the shaded area, okay, over the total number of pieces that are available, right? So here I have 1 shaded out of 2, so half of a pizza. We'll say that that's how much we're gonna eat, or maybe that's how much is left, right? Whenever I change the denominator, it's just like cutting the pizza. And I know this is a big review for some of you, but that's all right. Just be patient. So if I do this, right, now I have 4 slices of pizza. But notice, if it's the same pizza here, if I still have the half of the original, I can now say that I have 2 slices out of 4. So 2 out of 4 is the exact same thing as 1/2. All right, they're equivalent things. Okay, so if I have 2/4 and I subtract 1/4, now that I have the common denominator, remember that the denominator just stays the same throughout. 2/4 minus 1/4 equals 1/4, and that makes sense, right? Like if I subtract one of these, like if one of these was now gone, I would just have 1/4. All right, so that's kind of the math that's behind that fraction piece. Hopefully that maybe clicked for someone. So we have 1/4 x plus 1 is equal to -6. Sorry for the color change. So to get this x term by itself, I'm going to subtract 1 from both sides. So I'm left with 1/4 x equals -7. Okay, so to get this x by itself, I'm going to, so we started this off by changing this back to like 1/2 x, right? So what I want to encourage you to do at this point is to think about 1/4 x as x divided by 4, right? 1/4 of something is just dividing something by 4. So if you think of it like this, okay, and there's other ways to think about this, but if you think about it like this, then what you can do here is you can say, oh, x is being divided by 4, so I need to multiply both sides by 4 to get rid of that, right? So if I multiply 4 times 1/4, it equals 4 over 4, just equals 1. So it's just left with 1x, right? So what I have left here is x is equal to -28. Okay, so x is equal to -28, and we are done. The other thing you can think about is, okay, if you don't do that, the 1/4 is being multiplied by x, therefore I have to divide by 1/4. But we know that when we divide by 1/4, that's the same thing as multiplying by 4 over 1. Okay, so you could just figure it out that way as well. We're multiplying both sides by 4 over 1 to get rid of that 1/4, and then we have -28. Okay, so 1D. For this one, this is number 1 here. Don't get confused with that one. It's not 1.3c, I don't think, or maybe it is. Oh, it is 1. Sorry guys, 1.3c is equal to 3.3c plus 2.8. So I am going, this is just decimals now, right? So I've always said I like to move the smaller one over to the other side, which we could do here, but then we're left with nothing on that side, which doesn't really matter. I can show you guys that. So if we do that, if we do -1.3c, right, because this was just a positive, we're going to subtract 1.3c from both sides. Then here we're left with 0. If you have 1.3c's and you subtract 1.3c's, you're left with 0. 0 is equal to, and then in this case, this would just be 2c plus 2.8. Okay, in order to solve this, we have to move our non-variable term to the other side. Okay, so we can subtract 2.8 from both sides. So we're left with 2c is equal to -2.8. And then we have to get c by itself. So right now it's being multiplied. The opposite operation is division. So we get c is equal to -2.8 divided by 2. So if we divide -2.8 by 2, it means we're just cutting it in half. Half of $2.80 will be $1.40. So I'm going to think of it like that. And I get I'm saying a dollar now. 1.4 as my answer. Okay, feel free if you have to, if you want to check yourself, use calculators on that. But you can definitely do that mentally in your heads. So for 2a now, this is where it just gets a little more complex, like we did in that first example, example 2. Here we have to use our distributive property before we do anything. Okay, so this side, the left side is okay, but here I want to distribute. So I get 18, because 3 times 6 is 18, and then 3 times negative 2s is negative 6s. Now I just do the same steps. So I'm going to move this 6s out. So I'm going to add 6s to both sides. This goes away. This becomes 14s minus 10 equals 18. All right, so then I got to get this 10 out of here so I can get my s by itself. So we have 14s is equal to, add 10 to both sides, 28. All right, and then to get s all by itself, I'm going to divide by 14. So s is now equal to 2. All right, and if you plug this 2 back in here for these s's, you should get something that is equivalent. So let me just show you that really fast. 8 times 2 minus 10 is equal to 3 times 6 minus 2 times 2. Okay, so when I do this out, I get 16 minus 10 is equal to 6 minus, this is like essentially 4, right? So this is 6 minus 4, this is just 3 times 2. 16 minus 10 is 6, 3 times 2 is 6, and it checks out. All right, so you can always check yourself when you're on a test and you have a little extra time. For 2b, this one you just have to distribute both sides now before you do anything else, right? That's the only thing that's really new. So you have 7n minus 7 is equal to negative 6 minus 2n. Notice it's minus and not plus because it's negative times a positive, negative times a positive, so these are negative. Okay, so then I want to add 2n to both sides to get rid of that. So I have 9n minus 7 equals negative 6. I'm going to add 7 to both sides to get this thing by itself. So I have 9n is equal to negative 6 plus 7, which is 1. So then n is equal to, if I divided both sides by 9, 1 over 9. There is 2b for you. Let's keep cruising. All real numbers. So so occasionally, you guys, what you will get for a solution is that anything can work. Okay, so if you do that, basically what you're left with is an equation that is exactly the same on both sides of an equal sign. So here's an example. If you have 2 times x plus 1 equals 2x plus 2, if you simplify this out, you get 2x plus 2 equals 2x plus 2. Now let me ask you a question. If you were to plug in any number you choose a real number, a number in the real number system, any number, and plug it in for x, okay, you're going to get the same thing out on both sides of the equal sign. If I chose negative 1 million, if you plug in negative 1 million to both sides, on both sides of the equal sign, you're left with negative 2 million and 2. Right? So no matter what I plug in there, it's going to work. It's going to still make these two things equal. At the end of the day, with all of these, with all the ones that we've done until now, there's only one number that you could plug in that would make the two things equal. This last one, it was 1/9. If you try to plug 1/8 into n here on both sides, it would not work. They would not be equal. If you try to plug anything else besides 1/9 in there, it would not work, except for something equivalent to 1/9. So here, I could plug in whatever I want. I could plug in a 9th, I could plug in a negative million, I could plug in whatever number I want. It'll still make sense. So when this happens, we say that the answer is all real solutions, meaning I can plug in any number, any real number that I want, and this equation will always hold true for all things. Sometimes you get no solution. So that's when you solve an equation and you get a contradiction. So if you get something that's like 5 equals 2, and this is obviously not a true statement. This does not ever hold up. If you get a contradiction like that, you will have no solution. Let's look at example 3, and then you guys will be on your own. So these will either be all reals or no solution for example 3. Let's take a look. So we have, let's first simplify things, right? So we can do this out. So 7x plus 5x minus 5, I just multiplied. 5 times x, 5x. 5 times negative 1, negative 5, is equal to negative 5 plus 12x. So now I can combine like terms. Here on this side, I have 2x terms. I can combine them. 5 plus 7 is equal to 12x. Why did I not combine it with the negative 5? Because it's not a like term. So 12x minus 5 equals negative 5 plus 12x. Are those two things equivalent? Well, we can keep going here. If you're not sure if they're equivalent, like they look similar but they're a little different like this, you can keep going. So if I want to get my x's to one side, notice what happens. If I subtract 12x from both sides, this goes away on both sides, right? So then I'm left with negative 5 equals negative 5. You have the same thing on both sides of an equal sign. This is always true. This is always true. Negative 5 will always equal negative 5. Therefore, whatever I plug in for x in the original will always work. This is all reals. But let's look at 3b. So for 3b, let's distribute. We get 6y minus 30 is equal to 20 plus 6y. Here, if I keep going, I subtract 6y from both sides. Notice this goes away, but so does this. 6 minus 6 is just 0. So then I'm left with negative 30 equals 20. When is that the case? Never. This is an example of no solution. No matter what you try to plug in for y, these two things will never be equal. So this is an example of no solution. If something worked in here, if something could work in here, then we'd have a solution. If everything worked in there, then we would have all reals. But here, nothing can be plugged in there. So these two things were never balanced. Never balanced. Okay, nothing could ever work there. That's it for now, guys. We'll see you guys in class.